Continuing with our final exam review packet, we're going to review synthetic division and polynomials, factors, and zeros. This is fairly recent, so I think this should be a pretty simple section for you. So a reminder that when we are asked to find the value of a function, we're of course just asked to put that value of 2 in for the x coordinate. So of course you could just do arithmetic here. We could just take f of 2 is equal to 3 times 2 cubed minus 12 times 2 squared plus 2 minus 10. And of course you could grab your calculator and do that, and you would come up with the answer fairly quickly. Here we're going to use synthetic division for the same process, and it's really just a gimmick, another algorithm that does the same thing, and it might seem that the arithmetic goes a little bit more quickly. So remember that we bring down this first value, and then we multiply diagonally, and then we add the column, and then we multiply 2 times the next value, so we get negative 12. We add the column, and we'll come up with negative 11. We multiply, and here we come up with negative 32. And of course you could check the old-fashioned way with your calculator. We believe that this value, this remainder, is the y coordinate. So when we put 2 in for the x coordinate in this function, the y coordinate will be negative 32. So remember, another way of saying that is you've just found 1 point on the graph of this function. So the remainder, and if that remainder happens to be 0, then you found an x-intercept of the graph. So everything should fit together pretty clearly here. All right, in question 28, the rational zero test is the name of a theorem, and it tells us all the possible zeros that we could come up with for a function. And I just noticed another typing error in the packet, so we'll make sure we get this fixed. This last number shouldn't be 0, it should be 10. Okay, so our rational zero test tells us that any of the zeros that are rational numbers, in other words, any of the x-intercepts that are rational numbers, have to be factors of 10 over factors of 6. So our shortcut way of writing this was to put all of the factors of 10 in the numerator, both positive and negative, and all the factors of 6 in the denominator. And of course what we mean by that is many, many possibilities of combination. So for example, negative 5 over positive 2, or positive 2 over negative 3, or 10 over 1, or 1 over 6. So you can see that we'd have to do every combination from the numerator with every combination from the denominator. Okay, the next question says describe the end behavior, and what we learned is that when we choose an x value that is really large or really small on the negative side, and we raise it to the third power, it overpowers the other terms. So we look at the highest degree term and we ignore the others temporarily. And so we think, what happens if we choose a number that's a very large positive value? And of course 100 isn't a very large number, but we'll think of it to keep things simple. If we put 100 in for x and we raise it to the third power, of course it is positive. And then we multiply it by 6 and it is positive. And if we pick a number bigger than 100, it gets even bigger and bigger. So we can see that on the right-hand side. So this means as x moves to the right, the y coordinates go up. What happens if we put a negative number in for x? When we take a negative 100 and we raise it to the third power, it would stay negative. And then we multiply that by a positive 6 and it would stay negative. So what we know here is that the left end behavior is that the graph goes down. So the first term, the highest degree term, determines the end behavior. What do we know about the maximum number of zeros? Now, some of them could be double zeros, some of them could be irrational numbers, some of them could be complex numbers. So the zeros are not always rational, but in some combination, a third-degree polynomial can have up to 3 different zeros. Does it have to have 3? No. It could have 1 if it was a triple root. It could have 1 double root and 1 single root. So there's lots of different combinations, but it has a maximum of the degree. So a 5th degree has at most 5 zeros. So what about turning points? Well, if it can cross the axis 3 times, it can only turn twice. So think how a graph could cross the axis 3 times. If it crosses the axis 3 times, it can only turn twice. So this is n minus 1 for the number of turns of a polynomial function. Again, we're talking only for polynomial functions there. Okay, let's continue with question 29. Find all the zeros. Well, we know our rational zero test would tell us we've got factors of -8 over plus or minus 1 would be our only factors of this coefficient. So there aren't too many things that we would have to try here. Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, because our denominator is only plus or minus 1. So we know that we only have to test whole numbers here. We did have one hint that makes this problem easier to get started, and it doesn't work very often in the real world, but in the math test world, where we've got to get you through quite a few problems in a short time period, we like this hint. Notice that the coefficients add up to 0. So when the coefficients add to 0, then we know one of the zeros, it's a freebie, we know that 1 is going to work as a 0. So we do our synthetic division, and as expected, we get a remainder of 0. So in other words, we know that x minus 1 is a factor, and now we've got our reduced factor is x squared plus 2x plus 8. And we know how to factor that. Or if we don't know how to factor it, we know how to do quadratic formula. So I guess it doesn't factor. So let's do the opposite of b, plus or minus b squared minus 4 times a times c, all divided by 2 times a, which is 1. So we come up with, and we're going to put this over 2, and of course you can reduce that right away. And here we've got 4 minus 32, so square root of negative 28 over 2. So let's go up over here. Negative 2 over 2 is going to be negative 1. And the square root of negative 28, we're going to write that. This has got a 4 times 7, so we're going to bring a 2 and an I on the outside. So 2i square root of 7 over 2, and then you can see that we're going to cancel those 2's. So we've got negative 1 plus or minus I times the square root of 7. Let me write that a little more neatly. And we also had our 0 of 1. So notice that we had 2 complex zeros and 1 rational 0. And this is a good time to remind you that we learned that if a polynomial has 1 complex 0, then it has 2, because they will always travel in conjugate pairs. So if negative 1 plus I radical 7 is a 0, then so is negative 1 minus I radical 7. Notice that these two are not x-intercepts, so we would say that f has 3 complex zeros. Remember that real numbers are also complex, but f has only 1 x-intercept. So the complex zeros do not give us x-intercepts. So now we've just answered our first question in part A for number 30. If we know that some polynomial has 2, and this should say as a 0, not as a factor, there's one more typographical error. If 2 is one of its zeros, and 3 plus 2i is a 0, then we know that 3 minus 2i is also a 0. So the complex zeros always travel in conjugate pairs. So part B asks us what can we do with those factors then? Well, we could multiply them together and we could find a possible polynomial that has these zeros. So how do we go from zeros to factors? We subtract. So we need to distribute here. So we know that f of x, some function, would have these three factors. So how should we multiply them together? Well, let's leave this x minus 2 first, and let's do our distributive property here. So we'll keep the x minus 2 for later. Let's take x through this second polynomial, and notice that we could rewrite that, by the way. That might be smart if we distribute these negative signs first. We might be less likely to make an error. Distribute this negative sign. All right, now let's go ahead and distribute. So first I'm going to take this x and distribute it through this parenthesis. X squared minus 3x plus 2ix. And then I'm going to take the negative 3 and distribute it. And you could do this horizontally, of course. I'm going to line them up vertically. So we see here we got a negative 3x, and then we've got a plus 9. And then we've got a minus 6i. And then we'll use another color here to distribute the negative 2i. And notice what's happening here is, oops, I should go down a line. Works nicely every time that some of these terms will cancel, and then negative 2i times negative 3 will give us a plus 6i, and negative 2i times positive 2i is negative 4i squared. So look at what happened. These two terms cancel, and those two cancel, and those two cancel. And what do we know about I squared? It is negative 1. So this term will be negative 4 times negative 1. So in other words, what we've got here is x squared plus 9 plus 5. So it looks like we've got an x squared, plus 4, 9 plus 4. So now we're back into the real world. So when we multiply complex conjugates, they have a nice way of canceling out terms so that we get back to real numbers. And now we've got to distribute again. But now we've got much easier terms to deal with. So x all the way through. And then let's take negative 2 all the way through. And then we'll just rewrite in the correct order. X third comes first, negative 2x squared comes second, plus 13x minus 26. So let me remind you what we were doing here. We knew the answers. We knew 3 zeros. We knew the values that made it equal to 0. Every 0 came from a factor. And if we know the factors, then we can use distributive property to get us back to the polynomial. Here's a simpler analogy. If I told you that a polynomial had zeros of negative 2, 1, and 5, wouldn't you know that its factors were x plus 2, x minus 1, and x minus 5? So every time you're given a 0, you know that you can reverse its sign to put it back into its factored form. So that's all we were doing. We simply had to do that work with complex numbers instead of just with real numbers.